Hey everyone, this is part 2 of our lecture series on processing raw text. So be sure you go back and watch part 1 if you haven't yet. And this is part of my natural language processing course. So I wanted to do a quick reminder that when we're working on NLP, we're going to do this both in R and Python. So the very first thing that I actually did was set up my Python configuration. So I loaded the reticulate library and then printed out pyconfig here just so you can see that I'm using a virtual environment from reticulate, and it's calling my Anaconda 3 library. So I do assume that you have set this up, and once we get going here, there'll be some other things that I've already loaded in the first lecture that will be considered loaded in the second lecture, but I'll try to point them out here for you if you're only watching the second one. So the first thing we got through was actually sentence tokenization. So we've already covered regular expressions, how to remove noise from text, and we're working on tokenization. So let's look at word tokenization now. And it's probably one of the most important components in NLP work, because many of the analyses that we're going to learn how to do take what's called often a bag of words approach, where you treat each token or each word as an important piece to the analysis. So it's really important to get this part right. Now that feels like it should be really easy because you can just break words on white space, right? Like I can easily find all of the words here because there is a space between them. It's not so true in spoken text, where if you ever listen to a movie in another language, it sounds like they never breathe, right? Because we hear the word boundaries imposed by our brain, but often they're not actually spoken with space in between the words. But here what we really have to deal with is contractions. So we probably should look at that section first. By order of operations here, we'll talk about tokenization and then how to fix contractions in a few minutes. Then you have spelling errors, and then you have languages that are logographic or pictures. So there is no white space between the words, and sometimes each picture represents several key concepts. So you have to find a way to break those down into two pieces. Here we'll mostly focus on English, but remember that there are other languages with other considerations. Now at the start of each chunk here, I have a label of what type of chunk it is. If you're looking at the actual markdown document that made these slides, it's a little easier because it has the chunk type at the top. But once you knit that together, you lose that. So at the beginning of each chunk, I have what kind of chunk it is, just to help us keep track of the coding language that we're using until you kind of see those key differences between them. Another good way to know is that the code highlighting is mostly only for R. So if the code is like colored nice and pretty, it's probably an R chunk. All right, so in R, we can use tokenized words. This is part of the tokenizer package. Okay. And remember that clean text from the previous lecture is the cleaned up version of one of my blog posts. So we pulled that blog post from online, and now we're looking at can we break that blog post down into a usable format. Some arguments for tokenized words is to lowercase everything, which I'll leave on because generally we want to normalize the data into lowercase. Don't remove stop words because we're going to talk about stop words later. Do remove punctuation if you want. You can also remove numbers. I didn't in this scenario. And I could simplify this down into a vector rather than a list. There are some advantages to list format because if you're trying to kind of keep many text documents sort of together, so let's say you have 100 documents and you're trying to word tokenize all of them, but you want to keep the words with their own document, just leave simplify off because then you can unlist it in a way that allows you to keep document titles. If you just want all of the words and you don't care, turn that on and it will unlist, so it's now just a giant vector. So let's look at what that looks like. It's printed very long, but here is each of the individual words. Do notice that it broke apart my HTML links in here let's see, whatever. But you still have "I'll." So something like a contraction here, that's actually 2 words. We got to figure out how to fix that. And then let me make sure there's no more code on this page. All right, nope. We could also do this as the pen tree bank options. Okay. And we'll talk a little bit about pen tree bank in a second, but there's another function called tokenize PTB for pen tree bank. So with all of these functions that I'm showing you, remember that there are multiple options. Okay, so word tokenization is not like a one and done procedure, meaning that there are several different approaches to tokenizing words, and some of them deal with contractions and some of them don't. So clearly this option does not. So I'm really trying to give you a toolkit of starting where you can learn like, okay, there's this function called tokenize words. Okay, it doesn't quite do what I want it to do. Is there another option? Or how can I use regular expressions to supplement this option? So there are many ways to do this, is what I'm trying to say. So doing this with NLTK, we could also use the word tokenize package. So we're switching now to Python. And in R, it's tokenized words and tokenized sentences. In NLTK, it's the other way around. So it's word tokenize. They have a tree bank tokenizer as well. So pen tree bank is a really famous sort of corpus that is tagged and has lots of corresponding functions that have been trained on that tree bank. So this tokenizer was trained on the word sets from those, which allows us to build a really good tokenizer because we have a gold standard to compare it to. And we're going to get into learning how to build those kinds of tools in the next section. There's also the talk tokenizer and the regular expression tokenizer. Mostly I'm going to show you word tokenize, kind of keep it simple, because as you get better with your coding skills, you can really learn how to use the regex tokenizer. And then we'll also talk about spacy. So word tokenize is actually just a special instance of the pen tree bank tokenizer. Notice this is a Python chunk. Okay. I have already imported NLTK in a previous example. It is what I would jokingly call a regular expressions monster, meaning it was a lot of work that people put in to come up with all of the different kinds of ways that people can write words. I mean, it doesn't spell check, so you still have to deal with spelling errors, but it does handle many of the apostrophes and the word spacings and dashes that should stay versus shouldn't stay, so hyphens, periods for words like etc. and on. So learning regular expressions helps us understand what's going on in the pen tree bank tokenizer. It does focus on periods. It separates commas and single quotes when combined with a white space. Okay. Punctuation is kept and included as a separate token. And it sort of deals with contractions. And by sort of, I mean, here's an example where "I'll" is included. And it does break them out because of the single quotes with a white space, right? So it breaks them apart, but it doesn't fix the fact that that's actually "I will" or "I shall." It just keeps it as LL. So that's slightly problematic because we need the LL to actually represent the word it means. Okay. But the function itself is fairly easy. Okay, remember clean text is my blog post, so it's nltk.wordtokenize, and then you do clean text. And then I just told it to print a couple of the words so you could see what happened. So very similar functions between R and Python, tokenize words versus word tokenize. And they work almost exactly the same. You input a long string. So now I want to talk about spacy. We're going to use spacy a lot this semester because it is awesome, but as we go, you'll see that it requires a little bit more upfront work. So I included the link to spacy and some of their tutorials because this is really how I've been slowly learning spacy. And I wouldn't say that I know it very well, but I have slowly gotten the hang of spacy. So you will import spacy. Notice that the code is not colored here. So this is another good way to notice that we're switching to Python, is there's no real code coloring. Okay. Not for the function names anyway. All right, this here, this comment, this is almost the beginning of almost every spacy pipeline, is what they like to call it, where you will load what language model you want to work with. So we're going to load English to work with English. And if this particular line doesn't run, there are some tutorial guides on making sure that you have that particular model installed. But we're going to call it NLP. So this is just, if you look at the tutorials, this is the kind of thing you see. So I wanted to match that. So we're going to load the English language model. And these have been trained to do specific things like word tokenization. But the cool thing about these models is they've been trained to do much more than that. So a lot of the functions in R and NLTK are trained to do one thing. I tokenize words, I tokenize sentences, I do parts of speech. The thing about spacy is that these models are mini functions. So we'll do spacy process just to give us save the words equals NLP clean text. And remember, NLP is just what we defined it as right here. And then I told it to print this out. Now printing it out is the harder part, because once you process it, it actually processes a bunch of stuff. So it does sentences and words and all this other stuff at once for you. So we do spacy process dot sentences to get sentences dot sense. And that actually is in an iterator format, an iterator object. So I just told it to print out a list of them. And this is just necessary because I want to show you the output. And it worked pretty well. Okay. So we can see here are some sentences. Now I did break some of these on commas, I think. Okay. Oh no, the comma just means a new one. And then it says there are 98 sentences. So if you remember from the last lecture, when we were using some other functions, it said that there were probably 30 sentences. So spacy is clearly doing more breaking. Okay. And I think it does a really good job here with this code section that I was writing in this blog post, and it broke down each line of code as a separate sentence, which is kind of nice because those had hard returns, right? /ns between each one. And so now I can at least see that these are different lines in the document, that the writer of the document wanted them as separate lines. So they're not really all run together. All right. So it came up with 98 sentences in comparison to our 30 or so from the first half of the lecture, and it does run like completely off the page. So didn't print the best, but anyways. For word tokenization, okay. Now this looks crazy because it doesn't auto wrap here, but what we can do is talk a little bit about loops in Python. So loops, hopefully you've covered in your PyCharm assignments. If you're one of my people just watching this on my channel, I would definitely learn how to Python loop, because Python loops are really, really common. And PyCharm EDU has a set of tutorials that you can do for my folks in school. And so what I'm going to do is we're just going to break down this loop. Okay, so a loop includes for and in. Okay? So you want to do some sort of something for something in something. Okay? And if we read this going across, give me the word dot text. Okay, that dot text is part of the spacy code. So text is the key word here for give me back individual words. Okay, dot sense here is the key word for give me sentences. Excuse me. So dot text is the function to give me back my words in spacy processed. So essentially this would allow me to print out all of the words, and I'm just looping over them. So give me the words for words in spacy. Okay. Now the word here is made up. I could have said, give me cheese.text for cheese in spacy process. Now, spacy process does have to be an iterator object, and it is. And I remember here I said I had to do this list format because otherwise it wanted me to iterate. So here what we're doing is we're saying, well, we want some variable back, and to give it the text, loop over that variable in spacy. So inside spacy, it's looping over them. It's just calling it word, and it's giving me .text back. Okay. And I think there are probably better ways to explain loops, but as you see more of them, you will get the hang of the code. Essentially, you make up what the name of the variable is. So again, I could have called this X, could have called this, I don't even know. I love cheese examples. Could have called it Swiss, right? But the last piece, the N part, needs to be an object that you can loop over. If you aren't sure, try to print it out. If you print out the object and it says iterator, you're good to go. So I told it to print out the first 500 words. And we can see that it dealt these slash ins, remember, are hard returns, so we probably want to get rid of those. But then otherwise, it looks like it's working pretty well, right? Getting translations with RVS and Selenium, etc. So it is pulling and separating words fairly accurately. And you'll see some more of these loops as we go. So hopefully one of the explanations will click for you. All right, so another problem we can have when we're processing text is dealing with symbols. Okay. So there are definitely things that don't process correctly, or your machine can't read them, or you're coming from another language, or I don't even know. There's so many of these issues that can happen. And so for me, what'll happen is these special characters, especially when I'm reading in like abstracts for articles and the person's name, usually European, includes one of these, and maybe you don't want them, okay, or it's not meant to be there, or this is just how can I remove such things. Okay. And we'd want to normalize them to the language you're processing in. Right. And then sometimes maybe if I want to process German translated, and it left some of the little umlauts in there, it's the double dots. We don't normally have those in English, so I'd want to just take them out. There's a function in base R, ICONV. Okay. I like this function if you just want to strip them. So just like take them out. I think of it as labeled inconvenience. I know that's not what it means, but it's kind of how I was like, these symbols are inconvenient, take them out. But then that would mean that half of our words would be misspelled when maybe they shouldn't be. So instead, I'm going to suggest using the string I package because it's more of a replacement function. So this is kind of more of a regex rather than a strip. But if you just want to strip them out or convert, what the ICONV function does is convert between encodings. So I can go from UTF-8, that's normal for a lot of computers, to ASCII, to Latin, to Swedish. Like there's different types of encodings. And so encoding just tells it how the characters are coded. Okay. Unicode is very popular because it is for NLP people, because it does not matter what language it is. There's a special code for every type of symbol that you might see. So A is one symbol, a Chinese character would be another symbol, etc. I switched this to Latin ASCII because that works for me, but I would definitely think about what language you are processing text in, and then use the proper encoding for that. And it might take a little bit of work to convert all of the text to the same encoding. And so if you have a mix of different texts from different languages, I would suggest Unicode. UTF-8 is also very good for this sort of thing. So let's say we have these little characters that we want to switch. It's a little bigger. And I loaded the string I library because we haven't used it yet. And the function is string I translate general. So we've used string R, has very similar functions, but not this one. The string is in characters, that's just my variable name. And I want to translate it to Latin-ASCII. So here, this part, I would look at the help to help you determine which one, and I just like played with it until it looked right. Okay, so this was the one that made it look like what I wanted, and so now you can see that it's EAO without the extra symbols. And so that would help me keep from misspelling words. In other places and projects, I have used this function because what happened was it imported all of the dashes and the quotation marks as funky symbols. And I didn't want those, so I just removed them all out. All right, so how do I do that in Python? Well, Python, there's a specific package called Unicode data. Okay. And so I imported that. And we were going to write our own little function here. So def here means write my own function, define. Right? So this is like function X in R. And I'm going to call it remove accented characters. Inside a function, you just define what kind of variable you want to pass. So I could call this anything. I could call it cheese. However, I want to pass text through here. So we're going to just call it text to remind ourselves that it should include text. Colons. Now when you hit enter in Markdown, it doesn't do the spacing properly, so be sure you hit tab because everything that's underneath this function definition needs to be tabbed over. All right, then we're going to do the actual work here. So this one is a complicated set of functions on functions. So the functions in the Unicode data package, the first part is normalize. Okay, so we're going to normalize our text into this NFKD format. Then we're going to encode the text into ASCII, because that's what I would like. Then we're going to decode ASCII into UTF-8. Okay, so this actually will get us back to UTF-8. You could decode into ASCII as well. So the set of procedures is to normalize the code, encode it into a format you want to use, and then maybe decode it into the format you want to use. Okay. So I found this one by Google searching because I've mostly used just .decode, but this one really like helps us convert those characters in and out. So decode will kind of just switch everything from one format to another, but this encode to decode kind of pipeline allows us to change them from the accented characters to the Latin version first. So that's why this kind of normalize it, encode it from umlauts to not umlauts, and then decode that back into UTF-8 so I can have it in a Python happy format. So this will bring it back into English without the extra accents. Now, anytime you define a function, you need to return something, usually. So we're going to return text. Okay, so it's just going to give that text back. Okay. Once you run these kind of functions, they don't do anything because it's just waiting for you to use them. So now we can say remove accented characters, and I pulled that character set from R. So I just did r.characters to go from an R chunk to a Python chunk. And you'll see it printed out the same output. And remember, I didn't save my R characters, so it is actually it's doing the exact same thing to it because my R character variable is still the one with all the symbols. It's a little bit more work in Python, but I do think you get a little bit more flexibility on the encoding and decoding part, so I can kind of switch between all kinds of different types of ones. I do think Python handles Unicode a little bit better. So moving on, now into contractions. So we've talked about word tokenization, let's remove all the funky symbols, and then also deal with contractions. So what is a contraction? Well, it's a shortened or combined form of several words. So Yalav is one of my favorite ones. which is you all would have. Such a Southern thing to say. Where we've taken several words and kind of squished them together. So you see this I'll, we'll, where we're saying I will or we will. And so we have to find those and deal with them because there's actually two different words. Now, often these are words that would get eliminated when we think about stop words, but we haven't gotten there yet, so hold on to that thought. But let's say we have something like won't. Well, won't is will and not. So we can't simply separate on the apostrophe and fill in the word because this definitely wouldn't work. One and T is not really what we want. And they really present a lot of issues in processing text because you have to account for all the different combinations, and sometimes the combinations are ambiguous, especially using will versus shall. So I'll could be I will or I shall. Now, in modern day English, most people don't say I shall very often, so more than likely, probability wise, so when we started the semester, I said everything is about frequency, so more than likely people are saying I will, but there are some times where this is ambiguous and you just have to guess which one it should be. And so the best way to deal with them is to have a lookup dictionary. So a lookup dictionary just means like if you see this combination of letters and apostrophes, make it these two words. So if you see I apostrophe LL, make it I will. And this just allows you to tell it what it should expand to. And this idea is akin to having a lookup dictionary for text speak. So when text speak first started, they had these like pamphlets for parents, right? So what does LOL mean? What is my child saying, right? So it would say LOL, and then next to it, it would say, this means laugh out loud. So we could create a dictionary basically of all of their terms and their expansions. So acronyms present a similar problem. And if you're doing work that involves people using slang or like kind of text speak, you'd have to decide if you want to expand the acronyms or keep them as they are. Often I vote for keeping them because they're sort of a unique text token, but if you wanted to expand them, you could use a similar type process as what we're about to do. And it's a good thing people make these lists already, so we don't have to make our own, although you could add to your list. And that's what this says. So for special lexicons, so working with a colleague who wants to deal with Twitch. Okay, Twitch is an online gaming streaming platform rather, and people talk in those chats. So we're watching somebody play a video game and they're just chatting. But there's lots of specialized language used in those sorts of logs where people, when they're chatting, kind of are using their own shorthand. And so to really process that kind of data and make it interpretable to a non-Twitch person, you have to kind of make a special dictionary lookup. Especially for emoticons. So emoticons present a special problem because they come through as text, but sometimes they are not what you'd expect to see. So sometimes they're like little slashes. Sometimes they actually have their own code. So you got to figure out how to recode those properly. So we'll just focus on contractions before we get too deep into this is very complicated section. And so for R, there's a really cool package called Text Clean that we can use to deal with contractions. So I'm going to tokenize my words in my blog text, and I'm going to unlist that. So I just have this huge list of tokens. Okay, so these are all the words in my blog. And then I'm going to do replace all. So this is our regular expression replacement. Okay. And what this does is this solves a problem. This is mainly a Mac problem, but if you're on Windows, it never hurts. Okay. So there's the fancy version of There's the fancy version of an apostrophe, like that has the like kind of larger top, and then there's the straight up and down apostrophe. Macs do not like the fancy version of the apostrophe, So first thing I did was replace all of the fancy apostrophes with the not fancy apostrophes. And that just allows me to make sure that the next function we're going to use runs properly. And so I will almost always start many of my text cleanups with this sort of like, get rid of this stupid fancy apostrophe, because we don't want to eliminate it. We don't want to take it out because we need it, right? So the function we're going to use looks for those apostrophes. So we don't want to remove punctuation until after we've dealt with contractions. All right, so I just printed it out so you can see that it is the not fancy apostrophe. All right, so the function in text clean is replace contraction. Okay, nice and easy name. Replace it in our words list, so we have a vector of words. The contraction key is in the lexicon package, and it's called key contractions. This is actually the default option. I just thought I would show it to you so you could see if you want to update the lexicon, you can add to this key contractions. And then ignore case. At this point, we've probably lowercased much of our text, but I always just like to ignore case across all these documents because there are some functions that will auto-capitalize proper words, much to my displeasure. So anytime you can ignore case, it's probably a good idea. Although there are times when maybe you don't want to. So I'm just showing you that that's an option. And I told it to print out the same one so you could see and check this bad boy out. It went from lowercase, I'll, to I will, and then did it in uppercase. So it auto-corrected this to an uppercase I because by itself that should be uppercase. I would probably want to undo that just so that I don't have some of them uppercase and some of them lowercase. Okay. All right, so that's how you do this in R. In Python, we're going to do a similar type of thing where we're going to install a special package called contractions. And from that package, we're going to import their dictionary. So the Python functions work the same way, where we import a dictionary and we use that dictionary. So we're going to build our regular expression contractions function. Okay. So that function is going to use re, so we've imported the regular expressions library. Compile, meaning compile together. The join command with this little pipe in the middle. And put together all of the dictionaries and keys. So this kind of takes that dictionary and looks up all the keys for it. It kind of like puts them all together. So I should have really, honestly, I should have printed this out because what happens here in contractions re is it's a list. It's just like a giant regular expression. So it says I'll or he'll or because or won't or. The pipe here in regular expressions, remember, is the or option. So essentially this creates this just like giant regular expression that's like find any of these and do something with it. Okay. So next thing we're going to do is write a little function. Okay. So define expand contractions. We're going to see some sort of sentence or text here. Contractions dictionary should be our dictionary that we've just imported. Okay. So this is the default option. Inside that function, we're also going to define another little function called replace. And what it's going to do is it's going to find the match. So for that word, it's going to find the match in the dictionary and return that. If it finds a match in the dictionary, it will throw that back up and then replace it. So remember, read.sub allows us to substitute. So it will replace the replacement option with the original. Okay. So this is kind of like an embedded, not a loop, but an embedded set of rules. So if the match occurs, replace that match. Now, the only thing I would tell you to really change in any of this is if you are using a different dictionary. And so here I did expand contractions. I did this on my clean text. Now it does return the text as is. So we've got all these spaces because those are the /ns. And let me just scroll down a touch to where there was like an aisle. I think here, maybe this one. So it does expand them. So now there are no contractions. Now it's left all my R code alone, which is probably good. But now there are no more contractions that I can see. Okay. So which one's easier? Well, they're about the same. Because once you write this function, don't replace the wheel, or reinvent the wheel, rather. Weird phrase here. So don't work harder than you have to, and just use this function over and over again. A very smart person wrote this cute function, and it works great. So that's how I correct contractions in both R and Python. If I now have to deal with the rest of the problems that we see, and this is really going to be spelling mostly, but often there's other like things that people do when they're writing. So they might use extra letters. So I'm just going to call this slang. They might misspell words. We have to talk about stemming versus lemmatization. And then at the end, we'll also talk about bringing this all together. So anytime we have repeated characters, this is where regex really is the solution. Now, there are so many ways to do this. The nice thing about regex is it's so flexible, but we started this talk last time by also mentioning the bad thing about regex is that it's so flexible. And so I just picked one of the many options here that I thought was probably the easiest to understand regex-wise for people who haven't probably seen a whole lot of this. But do know if you kind of Google this and are looking at answers on Stack Overflow, there are lots of ways to deal with this problem. So let's say we have this really long text with lots of L's and Y's. Come on. So, please pardon the interruption. I had to let my dog in before she started barking at the door. All right, because she loves text cleaning. All right, so let's say we have lots of L's and Y's. And we want to get down to not that. We can use the string replace all function in the string R package. We'll put in the name of our text. We've used this function before at the beginning. Here's where it gets tricky, is this pattern piece. Okay, well, let me highlight. So what I'm going to do here is any alphanumeric character. Okay, this will also include digits, so you have to be a little careful here. You could do A to Z if you wanted to just do letters, but any alphanumeric character. Okay, so leave the parentheses around this. That's repeated more than once. Okay, so this is kind of like the star option where we talked about stars and pluses and question marks, but this one makes a little is important because of the replacement. So anything that's one plus, remember plus one or more of them, replace that with only one of them. Okay, so these two match. So if there's a bunch of them, replace it with only one of them. Okay. And you'll notice what that does here is for finally, it does actually misspell the word finally. There's not a good way around that, because then what we could do next is spell check the document. So we could replace all these and then spell check it and kind of fix it back. There are ways to combine those two steps together, but I think it's a little easier if we treat them as separate entities. And so I would just use this code over and over again, but basically it's any alphanumeric character that's one or more, replaced with only one of them. So it actually takes the F and replaces it with just an F. All right, in Python, not quite the same code, unfortunately. What we could do is take and use read.sub. Remember, this is going to substitute. Okay. R here for regular expression. Sorry. Wish it would let me highlight the text a little better. So R here for regular expression. Any character that's more than once, so that function maps here. We have to use 1/ instead of 2 because of the differences in language. Okay. So any letter that's repeated, replace that with only one of them. and do that in our long text. So remember, R and Python kind of do things backwards from each other. So in R, most of the functions say, give me the text, here's the pattern, here's the replacement. In Python, it's here's the pattern, here's the replacement in this text. And we get the same output. So the key thing here is these little /1s. Okay? One or more of them replaced with one of them, and it's kind of a placeholder. So it says, okay, any letter that happens more than once. Now spelling. Okay. The spelling options are varied. Okay, there are a good number of options, more options in Python, and I would say Python has the win here, because in R this is a little bit tedious. Of course, this is probably a package I'm not aware of, but in Python this is not so tedious. So small win for Python on this one. So it varies what you're going to do based on the package. And I would say there are different dictionaries, but definitely check what options it's suggesting. So don't totally do this mindlessly, because while the options presented are usually pretty good, they're not perfect. So let's look at this in R first, and I'm going to use the Hunspell library, which I've used for a couple of projects now. I really like it. It is what many open source projects use as their suggesters when you're like typing. I'm pretty sure Firefox does this. So I have a word list of misspelled words, and I say these words misspelled. Okay. So when you're working with Hunspell, the first thing you do is come up with the errors. So you make a little list, or not a list, it is a list, of misspelled words. So it'll find all of these are misspelled. Then I am going to say, well, suggest. Here's my misspelled words. Suggest me a set of options. Okay. You do have to unlist our spelling errors. And the dictionary is going to be US English. Okay, so you could actually do British English, and there are many more. So if you look at the help code for Hunspell, you can see that there are a bunch of options. Okay. Oops, got excited. So in my errors and my suggestions, and it's important that you save them as two different vectors. Okay. Well, these are lists, but save them, basically is what I'm going to say. In that spelling suggestion, what happens is it comes up with a set of options. So for these, there are actually several different options that word could be. It could be this, it could be these, it could be the. And it puts them in the highest probability order to the lowest probability order. Now here, what I've done with this line is pick the most probable answer. Okay? Now the most probable answer is not always the right answer. As you can see if you look at the output, it suggests the word the, which is more common than the word these, but that's actually incorrect. Okay? So I kind of just told it here, give me the most likely answer. But in reality, what I would probably do is look at the spelling suggestions and look at the errors and map them together. So I would create my own dictionary of, if I see this, replace it with that. Okay? But Hunspell is a great way to start to build that dictionary. So I've built a little dictionary, so I've just combined errors and suggestions together into one, and this is where I could write it out using write.csv and edit it myself if I needed to, which is what we did for one of our projects. And then I also added this piece here. What does this do? Well, what that does is it allows me to find all of my misspelled words, okay, spelling errors here, at the word boundaries. So here it's really important to make sure you only replace the misspelled words as themselves. So let's say that you had a compound word, right? And it included one of your misspelled words. Well, you don't want to fix that. So this allows you to fix misspelled words that are not internal to another word, okay? Where we're only replacing the entire word form and not half of another word. So here's an example. There have been times when I have accidentally told Microsoft Office to replace all of the letters IN, because I was looking for IN and was going to replace it with something else. Well, there are many words that include IN in the middle, and it just replaced it all in the middle of the word. So like linguistics includes IN, LIN, and it replaced it with, like LTHEG. And I'm like, oh, right. This allows us to not do that. This is in the string I package. Replace words using regex. The string we want to replace is our word list from up here. The pattern is our spelling patterns. Okay, so that's in our dictionary, and this is the pattern. This is our special code with word boundaries on the edges. The replacement is the suggestion. Okay, so essentially look for the error, replace it. Vectorize all equals false is nice because it just keeps it in the same format that you put into it. So here's a problem. These became the. This is just my warning that make sure that you are checking the output you're getting, because that is an incorrect translation. All right, how to do this in Python? Oh my God, it's so much easier. So way less code here, but the function, one of the packages that does this well is textblob. So from textblob, import word. Okay. I've got my word list here. And then here's our loop that we can to loop over each word and replace. Okay. Now this works well because this is already tokenized. So if you want to work with a document that isn't tokenized, you would need to do some regular expression replacements. And so that's one reason why this is so long, is this works if it's tokenized or not. This one works if it's already tokenized. So you have to do a little bit of work depending on the format that the document comes in. All right, given my word list, what I'm going to do. Right? So I am going to loop, I'm going to do some stuff for every word in word list. Okay, so if I ignore the first half, what this is doing is for every word in my word list, do stuff. Okay. That stuff, that function, is the capitalized word here. I should have maybe used a different word. So imagine cheese here. So for every cheese in word list, what you want to do is use the word function that we imported and suggest a correct answer. So if that word is found in the lookup dictionary, it will just suggest that it's already correct and will give it back to you. If the word is incorrect, it will give you the most probable suggestion. So this code also assumes that you want the most likely suggestion. There are other ways to see all of the options here. So this one's kind of already got that lookup dictionary built in. So in our words, give me the correct one back for every word in my word list. Now look at the differences here. So these became the. Words got corrected, but this one became disspelled. So each package will give you a slightly different dictionary lookup answer. And so I win for Python for being a little easier. I would tell you to look at the different options and pick which ones appears to work best for your text. So there's a new one called Deep Spell, which is based on some deep learning techniques that I think is probably pretty good. But the two I've shown you here are kind of cool, quick and dirty ways. Okay, so they're fast and they're pretty well known what their errors are. So the last set of concepts I want to cover is stemming versus lemmatization. Right, so what is stemming? So remember morphemes. We talked about morphemes before, where they're the smallest unit of meaning. Okay. So stemming is a regular expression procedure where you essentially just cut off or take off the stem, or sometimes called the inflection of a word. Okay. So let's say we got jump, jumping, jumps, and jumped. Okay. The smallest unit of meaning here is jump. Okay, that's the root word. Let's use that. And the stem is the ing, the s, or the ed. Okay, and those are morphemes. meaning jump is the morpheme and ing is the morpheme. So I know what the action is, and I know that it's a verb, present participle verb, right? Jumped would be past tense. So essentially what stemming does is it takes off the morphemes and you end up with the root word. However, this is a regular expression procedure, and so sometimes what can happen is it will chop off words that it shouldn't. And I wrote this example, and then as I ran the code, I realized it didn't actually do this. So there is one stemmer that does this. I think it's snowball, but not all of them do. But here's an example of something that can go wrong, where the word wings, like airplanes have wings, became the letter W only because S is a morpheme and ing is a morpheme, and it just lopped them off. And what you'll see as you play with stemmers is that it doesn't auto-correct the word back into its real form, it just literally cuts them off. And so that can be useful and it can not be useful. Stemming is easier, it's just a set of regular expression rules, but it doesn't always give you output that's interpretable. So if I compare that to lemmatization, lemmatization is where I use a dictionary to look up that jumped should become jump. Okay. A past tense of go is went, so it will say, well, went is the past tense, so it should become go. Okay. Stemming doesn't do that because went doesn't have a stem. Okay. So that's where it corresponds to a specific root word, sometimes called the lemma. So stemming creates a stem, lemmatization creates the original root word or lemma. Now, lemmatization can be quite difficult because often you need to know what part of speech the word is, because the part of speech will help find which lemma it should be. So wings is read as a noun, that means don't remove the ing, make it just wing, singular. And so for lemmatization, what you often have to do is first use part of speech tagging, then look up the lemmas based on their part of speech. That's not terribly hard, but it can be a lengthy, it kind of takes a while to run because we're doing multiple things at once. And there are some good kind of fast options, but a really good version of this is a little difficult to set up personally. So let's look at this in R. So here's our word list. Wings, jumped, morning, and reading. Okay. Morning is a word that should not get corrected because it's a noun. And I love TM. I feel like how have I made it so far into this lecture without using the TM package, but TM is a great package. And the function in TM is just stem document. It's nice and easy. Okay. So you put in your word list or your document, whatever string it is, and you tell it what language you want, and out pops the stems. Okay. So it fixed wings to just wing, jump to jumped. Morning, it chopped off the ing, and reading, it chopped off the ing. Okay. So morning here is a miss. In Python, there's actually two popular options. So I have my same word list. And from NLTK, I'm going to import Porter stemmer and Lancaster stemmer. Okay, these are written by different people. Porter stemmer slowly became the snowball stemmer, which is one of the most popular options now. Lancaster stemmer was written by the University of Lancaster, a team there, both very popular, both very good. They do slightly different things. And we'd really need to look at a much larger piece of text to see that they do slightly different things, because for the words that I picked, they do the same thing. So what we want to do is import them. Okay. These are functions, so we're just going to rename them as PS for Porter stemmer and LS for Lancaster stemmer. This is a common Python trick to shorten the name of the function. Okay. And then we have to do a loop. So as like I said, you're seeing a lot of loops. So for every word in my word list, stem it. Okay, using the Porter stemmer.stem, put the word in, stem those words. Okay, so you do have to have a tokenized word list. And we got back basically the same thing we got back from stem document. Okay, wing, jump, more in red. and we get the same answer for Lancaster stemmer. So I think stem document uses the snowball stemmer. Let's look. No, TM. All right. Nope, just kidding. It uses Porter stemmer. So of course we should get the same answer between these two. But then in the details it says snowball stemmer. So I think these are effectively the same thing now. But snowball stemmer is probably the one you'll see most if you like Google stemmers. So we get approximately the same answer, and it's approximately the same amount of easy here. I have a small win for TM. Okay, it's a little bit faster. Let's look at lemmatization. So the best way to lemmatize in R is not easy. Okay, it involves using tree tagger. Tree tagger is a separate program you have to install. Once I got mine set up, I hope I never have to do it again. But it's not terrible, it's just not easy either. But this would be like the gold standard of lemmatization. But we can probably get by with this text stem package. Okay. Text stem actually allows you to use the tree tagger options as well, which I found out a little too late for a paper I just wrote, but here we are. So if you're installing text stem for the first time, do know that you probably also have to install these corpus packages. And then it's nice and easy once you install it, and it seems to work pretty well. So I wrote like this intense code for using tree tagger for an appropriate lemmatizer, and then of course now later I find this one-liner. But I don't know, I have not played with this enough to know how well it works on lots of weird exceptions. But anyway, so lemmatize words is the function. And look, it works really well. Look, it kept mourning just fine. Oops, got excited. If I do this on a sentence, so my system keeps crashing. His crashed yesterday, ours crashes daily. It's from the textbook we're using. That actually works really well. My system keep crash, his crash yesterday, ours crash daily. Okay, so it fixed all of the different forms of crashes and crashing into one. So if you have to do lemmatization and you want it to be kind of quick and simple, I really recommend this text stem document package. It also has a stemmer, but I love TM. So let's look at that in Python. Remember that we imported spacy above, so this is going to use spacy. All right, so my same sentence, and I'm going to write a little function, lemmatize text. Process that with my NLP, remember that's spacy. And then here's where it does the magic. Okay, so with a space, it's going to join together the word lemmas. So this is where in spacy it finds those lemmas. If the word lemma is not a pronoun, okay, else just give me back all the words. Okay, so it replaces lemmas if you should, and then otherwise just gives you back the word that you had originally. And then returns the text. So when I do lemmatize text, my system keeps crashing. His crashed yesterday, ours crashed daily. It does add a little space here, but that's okay because that's what this is doing. If you don't have this little space dot join, it will run all the words together, which we don't want to do. So nice lemmatized text function that you can write using the spacy language processor that we built earlier. All right, last topic, stop words. So stop words are function words in a sentence, like the, and, a, of, and but. We can compare that idea to nouns. So nouns and verbs are the adverbs and adjectives, right, are the worker words in a sentence. Those are portraying the meaning of the sentence. So if I say, I went to the store, right, I and went, pretty important. That tells me what I'm doing. And where, the store. But to the store, to and the are not necessary. They help fill in the sentence in a way that allows us to understand the meaning, but aren't always necessary for processing for purposes of analysis. Now, there is a set of people who think about function words are important for lots of other things, but let's say you want to just count the number of sentiment words, right? So you want to do sentiment analysis, you don't need those stop words. So the removal of stop words here really depends on the next step, what our next piece to the analysis is. Because we want to hang on to those if we want to do part of speech tagging, they're important, but then later we might want to remove them. So the removal here kind of depends on where you're at. Okay. And the purpose of this lecture is really to show you how to do a lot of these things. And then once we get into actual processing, like named entity recognition and dependency parsing, we'll talk about when you apply them. So it helps if you know what stop words are. So later we can be like, now we're removing stop words. All right, and there are so many ways to do this in R. It's like unbelievable. I love it, but oh my goodness. So I'm going to tell you my favorite is TM. Okay, and there is a stop words package that that installs when you install TM, I think, and it has a dictionary list of words that people tend to remove. Okay. So we're going to use the SMART stop words, and this is about 600 words and contractions that can be removed as being not useful. If you just do kind equals English or you leave it blank, it does about 200 words. So there are different types of stop word lists. You don't really need this, I just thought I'd print it out and show you kind of what's happening. The function is lovely. Remove words in my sentence that are stop words. So my system crashed yesterday's, crashes daily. So we lost pretty much all the pronouns except my here. So we should have done some ignoring case options because my is definitely in that stop word list. So we should have lowercase this first, or I think there's a argument in remove words for ignoring case. Okay. And it just eliminated all those extra words. In Python, it's a little bit harder because we have to do this like kind of complex loop. But from NLTK, we're going to import stop words, and then it's got a very similar list. Right? So here's the NLTK stop words list. It has all these different contractions. Then it's not in alphabetical order, but a similar-ish list to TM stop word list. And then here's this giant loop. God bless. All right, so what is happening here? Give me the words back for all of the words in, here's this thing. So in my sentence, for the stop word function to work, I have to tokenize it first. So give me all the words back in my tokenized sentence if that word is not in our stop words list. So this loops over the sentence and looks at each word in the sentence because it's going to tokenize it and says, is this word in our stop words list or not? So we're going to get all the words back that aren't in our stop words list. And we can make this even better if we did dot lower to get this all in lowercase. So we get the same approximate list. Now it does hang on to the commas. Do we keep the comma before? Yeah, so both of them kept the commas. And we could join these together back into one big string, but effectively removed the same words. All right, so let's bring all this together. There is no one correct normalization procedure. Here are all the things that one should consider when processing text. So I think even the order that I did this lecture in is maybe not the best order to replace things in. I would start with contractions and spelling. I would take out all the funky codes, and then I would start thinking about stemming and lemmatization. So you should really do stemming and lemmatization after you've done all these regular expression replacements. If I work, I usually start with contractions and then I do spelling, and then remove symbols, and then I start to think about stemming and that kind of stuff. So sometimes things are required to be tokenized, sometimes not. So there's lots of flexibility here in what we can do. Okay. And each step along the way, I would examine the text. Okay. Make sure that I have done what I thought I was doing. So, did contractions, did it actually fix the contractions? Okay, great. Are there any other ones I need to fix with regular expressions or update my dictionary? Great, move on. Okay. And it also depends on the task at hand. So if I'm going to build a part of speech tagger, which is what we'll do next week, then I should leave in the stop words at the beginning because I need those to help me build my part of speech tagger. Okay. Then later, when I get to sentiment, I could drop them. So the order of operations also is going to really depend on what the task is, and whether or not you stem will depend on the task. Okay. So I would say in general, there's a lot of like small cleanups that you should do, dealing with the spelling errors and the like multiple letters. Those pretty much always apply, but things like stemming and tokenization depend on what's next. And so the purpose of this lecture is to really kind of say, here's a list of things that we have to think about. Look how complex this is. There's so many different considerations one needs to make. Then what we're going to do in the next couple of weeks is like for part of speech tagging, do X, Y, and Z, and then part of speech tag. So we're going to apply these to some of the ultimate goals, right? So once we get to sentiment analysis at the end of the semester, what we're going to have is like, okay, you know how to handle stop words. Do that now. Okay. So in summary, all of this together, including both lectures, what we've learned is that text is super messy and we have to find ways to clean it up. Even text that I wrote formally, which we use for my blog post, super messy. Okay. Slicing, calling parts of variables. So we just kind of did a quick kind of R Python discussion. Talked about tokenization, so how do we break things into sentences and into words. We looked at regular expressions and how those are like the key cornerstone to many of the functions that we are doing. We talked about how to remove symbols. We talked about how to deal with contractions, spelling, and sort of like chatting kind of issues. And then we ended with stemming and lemmatization as ways to reduce the number of types and tokens, and then we stopped with stop words, which is a good place to end, right? So again, this is a kind of list of things, but the order of doing them and which ones I do for each analysis is something we'll learn as we go. So you'll kind of figure out what system of normalization works best for you based on the task at hand. So next up is going to be part of speech taggers. We're going to talk about what that is and how those work. And if you're just here for the YouTube channel, thanks for listening.